Continuing with fractions, we're now going to be figuring out equivalent fractions, but this time we're going to be working on fully reducing. So basically that means that we're going to be using that division process to remove everything that we can. Whatever we remove from the bottom, we have to remove from the top. So the first thing that I want to do is talk a little bit about what a factor is, because notice the instruction for number 1 is write each fraction in lowest terms. And then it says use the process of dividing by common factors. Find the greatest common factor for each fraction. So a factor are numbers that multiply together to get another number. So, for example, I could rewrite the numerator 10 as its factors. So I know that 1 times 2 times 5 gives me 10. Now, I usually include 1 when I'm in the process of reducing, because sometimes everything but the 1 reduces out or cancels out, and so you have a 1 remaining. The main thing to know is that your numerator can never be empty. So if everything cancels, you need to put a 1, and this just helps me remember that there needs to be a 1 there if everything else goes. Okay, so I'm going to do the same thing for the 15. So I have 1 times 3 times 5. So the factors of 10 are 1, 2, and 5. 10 is also a factor, but that's not going to help here. But if you were asked for a complete list of factors, 10 would be included here. Factors of 15 are 1, 3, and 5, with 15 being another one. But again, we don't need that because we're in the process of reducing these things. So now I cancel the things that are the same, because again, when a numerator and denominator are the same, it equals 1. So I have 1 over 1. Well, 1 divided by 1 is 1, so those go away. 5 and 5, right? 5 goes into 5 one time. 5 goes into 5 one time. And then I'm multiplying, right? So I get 2 times 1, which is 2, over 3 times 1, which is 3. So you can use the ones or not, as long as you remember that the 1 has to be there if there's nothing remaining in the numerator. Okay, so for B, let's go ahead and use that same idea of identifying factors of 12 and also 36. Okay. Oh, and actually, let me back up, because I did add this part where it says find the greatest common factor. So that's the biggest number that goes into both of these, right? So in this case, the 5 went into both, and there's no number bigger than that goes into 2/3, okay? Or that goes into both 10 and 15. So that means that my GCF, or my greatest common factor, is 5. So GCF, the biggest number that goes into both the numerator and denominator. Okay, so now let's move to B. So if you know your factors, you can jump straight to the greatest common factor. All that means is you have fewer steps that you need to do. But because this says to divide by common factors, you can pick any common, just as long as you get yourself worked down all the way to when it's fully reduced. So when you're asked for dividing by common factors, you have flexibility as to which ones you're going to use. Okay, so I'm going to start by writing out some factors of 12. So I know that 2 times 6 gives me 12. Now 3 times 4 also gives me 12. So you could use that. And then this one, let's see here. So I know that 6 times 6 gives me 36. So notice here, I have 6's that are the same. Okay, so I'm going to cross those off. But then, is there another common factor? Well, I see that 2 goes into 2 and 2 goes into 6. 2 times 3, right? So that was my factored form for 2, 6. And now the 2's go away. So I'm left with 1/3. So that took me 2 steps. But what about that GCF, that greatest common factor? Well, I want you to look at the numbers that canceled, okay? So we had 6 here that canceled, and we also had a 2. So that means my GCF is 6 times 2. So the first number, right, that canceled out times the second number that canceled out, and that gives you your GCF. So let's say, just for kicks, that we went back and instead of doing the 2 times 6 and the 6 times 6, we went up here and we said, okay, well, we know that the GCF is 12. So now I'm going to divide top and bottom by 12. So notice this is basically what we did previously, right? We're finding an equivalent fraction. But in this case, we're dividing by the largest number possible. 12 divided by 12 is 1, and 36 divided by 12 is 3. So that method you would use if it said to fully reduce or get your fractions into lowest terms using the greatest common factor. But in this case, again, it says common factors, so you have flexibility as to which ones you use. Okay, so go ahead and pause the video and try C and D, both getting them into lowest terms and then also finding out what that GCF is. All right, so for C, looking at this, I am going to, let's see here. So I know that 5 times 6 gives me 30. And I also know that 5 times 9 gives me 45. So I'm just going with factor pairs, so numbers that are multiplied together to get the numerator and denominator. And I'm going with the factor pairs that just come to mind first. Okay, so I happen to be more familiar with 5 times 6 and 5 times 9. Now, if I were to do that and I didn't have any visible common factors, I would just break things down more. So I'll go ahead and make sure to show that to you later in the video. Okay, so the 5's go away. So I'm left with 6/9. Now, something else goes into those, right? That is common. So this, let's see, can become 2 times 3 and 3 times 3. Those go away, and I'm left with 2/3. Okay, so that's my fully reduced fraction. Now my GCF, right? Well, 5 canceled and 3 canceled. So my GCF is 5 times 3, which is 15. Now to check that and to see how you could use that, right? It would be 30/45. I'll go ahead and put a box around the 2/3 so it's easier to see that that was the fully reduced fraction. But now, instead of using just random factor pairs, right, I'm going to go ahead and show that I'm dividing by the GCF, the greatest common factor, which is 15. So 30 divided by 15 is 2, and 45 divided by 15 is 3. And that is your final answer. So again, it's nice to identify greatest common factors, well, because they're greatest and it takes fewer steps. But if you're not asked for that, you don't have to use the GCF to factor. You do, however, have to make sure that everything is as reduced as possible. So that may take a few rounds of reducing. Okay, so for D, Some numbers we may be more familiar with than others. Okay, in this case, 65 and 115, we may not be that used to, right? Not numbers that we stumble upon that often. So there are numbers at the end of each value in the ones place that can help you identify at least one thing that can go into it. So anytime you have numbers that end in 5 or 0, you know that 5 goes into it. So that's what I'm going to start with. I'm going to go ahead and show, and again, I know 5 goes into it because 65 ends in a 5 and 115 also ends in 5. So I'm going to divide both of those. Okay, and then 65 divided by 5 is 13. Okay, and then 115 divided by 5 is 23. Now, if you were to try to find factor pairs for those, the only ones that exist are 1 times 13 and 23 times 1, or 1 times 23. These are prime numbers or prime factors. Okay, so prime factors refer to factors that are only divisible by 1 and themselves. Okay, so 13 equals 1 times 13, 23 equals 1 times 23, and those are the only options. So we know that 13 and 23 are prime. And we'll be working more and more with how to identify prime factors and how useful they can be for making sure that things are fully reduced. All right, now going back to the GCF, right? The only number that was common between the 65 and the 115 was 5. So the GCF is 5. And that is your final answer. So don't forget that term prime factors or prime numbers, right? And then prime factors are numbers that go into others that happen to be prime. All right, so here we have find the fraction in lowest terms for each scenario. So lowest terms means that if we can, we need to reduce our final answers. Here, we need to write the information that we're given as a fraction. So how do we do that? So the beginning of this says there are 4 quarts in 1 gallon. This value, the first value, is always the numerator of your fraction. Okay. And then that is over the second value, which is 1 gallon. Okay, now I'm including units because I have to include units in my final answer. If there's any chance that I'm going to forget the units, I would go ahead and just write them in to begin with. Now, it's what is the fraction of quarts? So we don't know, we don't know what's in the numerator, right? That's what we're trying to find, but they've given us 5 gallons. Okay, so we are trying to find that value. Well, hopefully that looks familiar from something that we've done before, right? Where we mathematically find equivalent fractions. So I'll clean this up just a little bit and go ahead and rewrite this without units because that's how we've seen these before. We just have to remember to include them in our final answer. So the question is, how do I get from 1 to 5 using multiplication because I'm going from a smaller number up to a bigger number? So I multiply by 5. If I do one thing to the bottom, I've got to do it to the top. So I multiply by 5 and I get 20. So it's 20 quarts, right? Because that's the unit that's in the numerator, to 5 gallons. Okay, so in this case, the lowest terms doesn't actually apply because we started with the lowest terms and we were creating a fraction that included the relationship of how many quarts to 5 gallons. So your final answer is 20 quarts per 5 gallons. All right, so looking at this next one, we have what fraction is 30 seconds of 1 minute? Well, here we're just taking a relationship that they've given us and writing it as a fraction. So what fraction is, again, here's the first value. So we get 36 seconds per 1 minute. Okay, that's the fraction. We don't have any change in units. We're not going from one amount to another. So that shows the fraction of the 30 seconds to 1 minute. Okay, so now moving to the last one here on this page. If you're moving along with the notes, right, this will be the last one on the first page of this section of notes. So here we're being asked for prime factors. So we already talked about prime factors, right? It was 13 and 23. 13 went into 65 and 23 went into, I think it was 115. Anyway, those are prime factors, prime numbers that go evenly into something. So how do we find prime factors? We're going to use something called factor trees. So for factor trees, we take the number that we're given, so 45 in this case, and we think about two numbers that multiply together to get 45. There are multiple options. So the way that you get down to your final list of prime factors may be different, but as long as you're using factor pairs that are correct, you will ultimately get to the correct final list of prime factors. So I'm going to go ahead and start with 9 times 5. Well, 5 doesn't have any other factors besides 1. So 1 times 5 is 5. That means that 5 is a prime factor. But 9 has additional factors, right? So I can also get 9 by 3 times 3. Well, 3 is only divisible by 1 and itself, meaning it's prime. So I'm going to go ahead and put boxes around those. So all of the prime factors of 45 are 3 times 3 times 5. It's always nice to be able to check your answer. When you've found a list of prime factors, the way that you check it is by multiplying the prime factors together. If you've done it correctly, it should get you back to the original number. So I'll go ahead and show you that. So 3 times 3 is 9 times 5. 9 times 5 is 45. So that checks that 3 times 3 times 5 are in fact the full list of prime factors. All right, go ahead and try or pause the video and try 150. Get all of your prime factors using the factor tree. Go ahead and then go ahead and go through the process of checking your answer. All right. Now, anytime a number ends in 0, I know that 10 is one of the factors. So I'm going to go ahead and use that fact to figure out the first factor pair that I'm going to use. Now, numbers with a 0 are also divisible by 5, so you could use that, right? But I just tend to use my multiples of 10, so numbers that 10 go into 10, 100, 1,000, and so forth when I can. Okay, both of those are not prime factors, so I need to bring each of those down at least one more step. So 15 has a factor pair of 3 and 5. Well, 3 and 5 are prime numbers, so I'm going to put my boxes around those. And then factors of 10 are 2 and 5. Well, both of those are prime. So my final list of prime factors is 2 times 3 times 5 times 5. We'll go ahead and check that, but I do want to mention that when I write out my factors or my prime factors, I usually do them in numerical order. And this helps for when we start using these factors to reduce fractions. So I just wanted to mention that now as to why I keep doing that. And then I'll show you the benefit of it when we get to reducing fractions. Okay, so I'm going to go ahead and check this. So 2 times 3 is 6, times 5 is 30, times 5 is 150, which gets me back to my original. So that confirms that the 2 times 3 times 5 times 5 is absolutely correct. Okay, so here's an example. I mentioned, right, that I'm going to show you how writing in numerical order is helpful when you're reducing fractions using prime factors. I'm going to go ahead and show that to you here again. Now, prime factors are what you can use if you're unsure whether a fraction is fully reduced. I don't know about you, but sometimes I'll be going along, right? I'll get to an answer and I look at it and I'm like, I don't know, is that fully reduced or not? If you're not sure, go ahead and pull out your factor tree process, because you know if you've canceled out all prime factors, your fraction is fully reduced. So I love prime factors for that. Okay, so now I'm going to go ahead and figure out the factors for the denominator. So I have 50, well, 2 and 25 go into 50. 2 is a prime factor. 25 is not prime, so I still need to take it down one more. And that is 5 times 5. Now notice that I'm putting boxes around my prime factors. The reason that I do that is it's really easy to actually accidentally drop a factor if you don't have something marked. Okay, so make sure that you include those so you don't accidentally drop something as you're recopying. Okay, so the next thing I'm going to do is to rewrite my fraction using those prime factors. So the numerator I'm going to write as 5 times 5, and the denominator I'm going to write as 2 times 5 times 5. Now I look to see what's common. Well, the 5s are common, right? And these 5s are common. So if I write what's left, I have a 2 in the denominator, but there's nothing left in the numerator. So remember that I said you cannot have a blank numerator. So if there's nothing left, it means that there's a 1. It just means that everything canceled on top, right? So 5 divided by 5 is 1. I'll show that to you mathematically, right? 5 divided by 5 is 1. And so if you multiply on the top 1 times 1, you get 1 in the numerator. 2 times 1 is 2. All right. So go ahead and pause the video. Try 4B. Oh, after. I keep forgetting this part. This is why it's always good to double check the instructions when you're reading something. So it says find the GCF for the fraction. So again, the GCF is what is the number that was canceled in each, right? So here we have a 5 and another 5. So the GCF is 5 times 5, which means your GCF is 25. Now, because it specifies using prime factors to reduce, you have to use this process. So previously it was use common factors. Now it's use prime factors. So that detail is really important. Okay, so now go ahead and do your factor trees, reduce the fraction, and then figure out what your GCF is before you're done. So go ahead and pause the video and go through those steps. Okay, so once again, I'm going to pull out each number. So think of this as two separate factor tree problems before you put everything together. Okay, so let's see here. Let's do 3 times 8. Sure, why not? So 3 is prime. Now 8, right, is 2 times 4. 2 is prime. And 4 is not, so I need to take it down even further. So I have 2 and 2. Well, now I have a full list of prime factors, and at any point, if you want to double check that they're right, you go back and do your reverse multiplication, right? 2 times 2 is 4, times 2 is 8, times 3 is 24, so that list is complete. And now I'm going to go ahead and pull out my 72 and do the same thing. Now, any number divisible by 0, 2, 4, 6, and 8 are all divisible by 2. So I at least know that I can divide 72 by 2. So I'm going to go ahead and do that. And I get 2 times 36. If you're not sure, do 72 divided by 2 and you'll get 36. So you can figure out what the other part of the factor pair is. 2 is prime. 36 is not prime. So I'm going to do, let's see, how about 3 and 12? Well, 3 is prime, so I can't take that one any further, but 12 is not. So I have, let's do, how about 3 and 4? 3 is prime, and then 4 is not, so that goes down to 2 and 2. You can do your quick check, remultiply everything, and make sure that we get back to 72. At this point, we now need to rewrite our fractions using those prime factors. So I'm going to go back up here. Here's my fraction line. Then I'm going to use this list of prime factors to rewrite. And again, if you want to double check, multiply those together, make sure that they equal 24. It's always good to practice, because if we don't practice these things, when we get to a test, we're not going to remember them. Our brain just can't hold on to that much stuff, especially if we have any extra anxiety because of the test. I don't know about you, but math tests used to really be scary for me. I still don't love them. But yeah, recognizing that and preparing for the increased stress that you may feel is really important. And one of those things is using these strategies of checking your answer anytime you're doing problems, so it just becomes second nature. You don't end up having to think about it. You just do it automatically. Okay, so I want to write these in numerical order, so I'll go ahead. I'm just double checking by crossing these off that I didn't forget anything in the numerator. So now I'm doing the same thing in the denominator. I'm doing them in numerical order. So 2, I've got another 2 here, another 2. And then I've got 2 3s remaining. So that looks to be complete. So now I'm ready to cancel. And again, I cancel anything that's the same or common between the numerator and the denominator. Okay, so those 2s, those 2s, those 2s, and those 3s all cancel. So what I'm left with is an empty numerator and a 3 in the denominator. So that empty numerator means there's a 1 there, right? Because everything canceled down to a 1. I didn't show it, but this was the same as all these things, right? Simplifying down to a 1. So 1/3 is your fully reduced fraction using prime factors. So how about that greatest common factor? Well, I have 2's were crossed off. Times 2 is 4. Times 2 is 8. And times 3 is 24. So my GCF is 2 times 2 times 2 times 3, which is 24. So the numbers that got crossed off or get crossed off, you multiply them together and that gives you the GCF. All right, so go ahead and pause the video. Try C and D using prime factors to reduce and make sure that you use that factor tree. And then once you've done that, figure out what the greatest common factor is for each fraction. All right, so these numbers are just getting bigger, which means organization is that much more important. So these strategies of putting boxes around your prime factors, crossing prime factors off as you put them into the numerators and denominators, doing them in numerical order, all of those things will help you deal with the fact that numbers are getting bigger. All right, so step 1, I guess I'm doing green. Sounds good to me. All right, so 10 goes into this because it ends in a 0. So I have 12 times 10. Neither of those are prime. So I have, let's say, 3 and 4. This is 2 and 5. So now I'm going to go ahead and box those off because those are prime. 3 is also prime, but I still have the 4 that I need to break down, and that becomes 2 and 2. All right, so I don't see any other numbers that can be taken down any further. So now I'm ready to move to the denominator, which is 270. Same thing, it ends in a 0, so I'm going to go ahead and do 27 and 10. Well, 27 is 9 and 3. 3 is prime, 9 is not. So I get 3 and 3. Those are prime, so I box them off. Okay, and now that 10 isn't boxed off, so you can see here why those boxes are so helpful, because there's a number there. It doesn't have a box on it. That means I still need to keep going. Well, factors for 10 are 2 and 5. So I'll box those off, and now everything is dealt with. Okay, so I am now going to go up here and rewrite in numerical order the numerator and the denominator. So I get 2 times 2 times 2 times 3 times 5. Now, it is not wrong to not write them in numerical order. However, I've found over the years for myself and also for other students, those who don't write them in numerical order have a much higher chance of making a mistake. So it's one of those easy things that can make a big difference. All right, so this time I have 2 times 3 times 3 times 3. I still have a box here that isn't crossed off, so that is times 5. Okay, ready to cancel. So 2 is common. Let's see, there's nothing for those 2's to cross off. The 3's cross off and the 5's cross off. So what I'm left with when I multiply is 4 over 9. So that is my fully reduced fraction. Now the GCF, again, are the numbers that were crossed off. So 2 was crossed off, 3 was crossed off, and 5 was crossed off. So 2 times 3 is 6, times 5 is 30. So my GCF is 30. All right, now I've got 143 and 121. Both of these numbers may be less familiar. So it's important to have a strategy, right? Where, what do I do if I don't recognize the numbers? What do I do if I look at those last digits and it's not divisible by 2, not divisible by 5, not divisible by 10, right? What do I do? Well, hopefully you'll get to the point where you do recognize the factors in these numbers. But let's say that you didn't. It's okay, we can still figure this out. Now, 121, let's just say, for example, that number is one that you feel more comfortable with. Okay, so if you're familiar with the factors of 121, you would know that 121 comes from 11 times 11. Okay, well, that means that if something can reduce with the 143, it has to be an 11. If it's not an 11, there's nothing that can be reduced, right? So instead of going through 143 and starting at 2, right, divide by 3, divide by 4, instead I'm going to take this factor and see if it goes into 143. So 143 divided by 11, okay, if that gives me a whole number, then it means that 11 is a factor. Well, that gives me 13. Well, notice 11 is a prime factor and 13 is a prime factor. Okay, so the strategy that I just showed you keeps you from having to try all these different numbers. Now, if you didn't know any factors, I would just start with the smaller number and figure out what factors start at 3, 4, 5, whatever you need, work your way up, and eventually you would get to 11. And then you would say, okay, right, what we did here, 11 goes into 121. Does 11 go into 143? Okay, so now I'm going to rewrite. So we figured things out a little differently here, right? I didn't actually use a factor tree. So 121 is the same as 11 times 11. And then 143 is 11 times 13. That's what I figured out here. My 11s cancel. And so my final answer is 13 over 11. Now we'll be talking about this a lot more, but I just wanted to mention that when the numerator of a fraction is bigger than the denominator, it means it's an improper fraction. So what we do with those, and really what they mean visually, is something that we'll talk about later, but I just wanted to mention that because it may look really unfamiliar, but it will become more familiar as we work with them.